We're now going to discuss further properties of continuity, and in particular, I'm going to be concerned about the continuity of a function not at a single point, but let's say on an interval. Maybe it is an interval of a finite length, maybe it's an interval of an infinite length, closed, open, doesn't matter. So if I have a function that is continuous on an interval, I want to understand what sort of common properties continuity will satisfy at all points of the interval. And I will illustrate first what I'm trying to say here by considering a few examples, and then we're going to introduce some new continuity-related notions. Before doing the examples, let's just recall a few definitions related to continuity. So I'm going to recall that f is continuous at some point x0 inside the interval I if, now we have two choices. Either we can use the sequential definition of continuity, or we can use an epsilon delta definition of continuity. And I'm going to stick for now with an epsilon delta definition, with the epsilon delta definition. So if for any epsilon greater than 0, let's use functor notations, there exists a delta greater than 0 such that x minus x0 being less than delta, and of course x should belong to I, this would imply that f of x minus f of x0 if this difference is less than epsilon. Right, so that is fact number one that I would like to recall. So definition of a continuity at a point. And number two, we say that f is continuous on the entire interval I if f is continuous at every x. Let's say x0 in I. Right, so if I'm saying that if I combine 1 and 2, if I'm saying that f is continuous on an interval I, that means that I can verify this definition that I stated here at every x0, right? Okay, so if all of this is true, then let's observe one thing here. So I'm saying that f is continuous on I if it is continuous at every point x0. As I just said, that means that I can verify the epsilon delta definition at every x0. But because I'm going to verify it separately at every point x0, that means that if somebody gives me an epsilon, then in principle delta is going to depend on where I'm checking for continuity, at which point x0 I'm going to look. So let's note then, before we do examples, note that for a given epsilon, delta would generally depend on x0. Okay, and now let's test this statement on examples as promised. So let's look at the example number 1. Let's consider f of x equal to x squared on the interval from -1 to 1. Let's say not including -1 and 1. And I want to show as we have already done some time ago, I want to repeat this here. I want to show that f is continuous on, instead of me writing -1, 1, let's label the interval as I. That f is continuous on I by using the epsilon delta definition. Of continuity. All right, so let's, in order to show that the function, again, is continuous in an interval, I pick a point inside the interval, an arbitrary point, and I need to show that the function is continuous at that arbitrary point. So choose any x0 in I. Then what do we want? We want to find all x, or in fact we want to find delta greater than 0. Well, again, I'm ahead of myself here. Given an epsilon greater than 0, I want to find the delta. Okay, let me finish rearranging here. So I want to find the delta such that epsilon delta definition of continuity is going to hold. So such that x minus x0 being less than delta implies that f of x minus f of x0 is less than epsilon. And again, an important caveat here is that x must belong to the domain of the function x, function f. So let's insist on x being inside the interval I. Okay, so let's see how we can proceed here. Remember also that for questions like this, sequential definition of continuity actually would probably be easier to use. But in this case, I want to concentrate on epsilon delta definition, and it will be clear why soon, why I want to do that. Okay, so we picked an epsilon greater than 0. So we want f of x minus f of x0 being less than epsilon. F of x is x squared. So we want x squared minus x0 squared to be less than epsilon. Okay, so how can we make it less than epsilon? Of course, what we want to do, we want x to be sufficiently close to x0 for this to happen. So let's try to massage the expression as we typically do. So absolute value of x squared minus x0 squared I can write by using some algebra as x minus x0 times x plus x0. And I want that to be less than epsilon. Of course, this might not be an optimal thing to use because this would mean that I want, in fact, let me just add one more step here. I can write this as absolute value of x minus x0 times absolute value of x plus x0. And now if we observe that both x and x0 are in the interval between -1 and 1, the largest absolute value of x plus x0 can be is 2. So this is less than 2 times x minus x0. And now if we request that this is less than epsilon, that this will be equivalent to saying that we want x minus x0 to be less than epsilon over 2. And so if we set delta to be epsilon over 2, then we're done because the implication goes both ways. So then x squared minus x0 squared is going to be less than epsilon as long as x minus x0 is less than delta. So one thing to note here then is that, so we proved continuity, the continuity at all points. So we should note that the same delta works for all x0 in I, right? Meaning that if I change x by the same small amount, doesn't matter where I am inside the interval I, then f of x is going to change by the same controlled amount in return, right? Changing x by delta will change f of x by no more than epsilon. So then, in a sense, what we have is a statement about the rate of change of our function, right? It kind of changes at all points slower than the certain rate. And then if this is a statement about the rate, let's see what else we can say, or how else we can express the same, somehow the same idea. So also, something that we have not really done yet here, but we have done in the Calc 1. So the rate of change of the function f is f prime of x, right? So in this case, f prime of x is 2x. And so therefore, on I, the fastest magnitude of the rate of change is going to be actually 2 in this case, right? Because x in this case belong to the interval from -1 to 1. And if the rate of change, instantaneous rate of change, is no more than 2, then f of x minus f of x0 this must be less than 2 times x minus x0, right? If the any rate of change on any instantaneous rate of change on interval from -1 to 1 is less or equal to 2, actually less than 2 because we're an open interval from -1 to 1, then we expect that the slope of any tangent line or any secant line connecting 2 points x0 and f of x, x0, f of x0, that slope is going to be less than 2, and this is the same statement, right? And then if I want f of x minus f of x0 to be less than epsilon, what do I need? How do I need to change x, or what size of x minus x0 to the 2? It should be the amount which is less than epsilon over 2, right? So if x minus x0 changes by less than epsilon over 2, then f of x minus f of 0 is going to be less than epsilon. And this is kind of the same result as we have just gotten, right? So that means that, like I said, the statement of delta being independent of x0 is somehow related to how fast my function is changing. All right, so that is it. Actually, let me do yet one more thing. So these are just some comments that I want to list here. So if just writing what I said a moment ago. So if x minus x0 is less than epsilon 2, epsilon over 2, then this difference is less than epsilon. Let's do the same thing graphically. So graphically, if we sketch the parabola, right, that's our function x squared. It's not a very good parabola. So we have a function x squared between x equal to -1 and x equal to 1. And then I have 2 points. I have x, 0, and x. So f of x and f of x0. Then just like I said a second ago, right? So if I am looking at the slope of the tangent line between these 2 points, then from a graph, it's obvious that the highest slope is going to be at 2, right? So therefore, f of x minus f of x0 divided by x minus x0, this is less than maximum slope of the graph, which is equal to the slope at x equal to 1. And that is equal to 2, right? So that's the same thing as what I got in my procedure for finding delta from epsilon and by computing the derivative. All right, so that is a situation number one. Now let's look at the second example. And the second example is going to be as follows. Let's consider exactly the same function, f of x equal to x squared, and I, the interval, is going to be an interval from 0 to infinity. And I want to answer the same question. I want to show or actually use the epsilon delta definition to show that f is continuous on I. All right, so we approach this in the same way. We need to find, first of all, I'm going to fix any x0 in I and choose any delta greater than 0. So what I want to do, I want to choose any epsilon greater than 0, sorry. I want to find then a delta greater than 0 such that x minus x0 less than delta will imply that f of x minus f of x0 should be less than epsilon. Basically exactly the same thing as I did before, with the same function in fact, and the only thing that I'm changing is a domain, right? So I'm looking at the interval from 0 to infinity. Okay, so then the same computation should apply. So let's, so we want to find a delta like this. So therefore, we're going to look at x squared minus x0 squared. I want that to be less than epsilon. So we can once again factor things out and use a property of absolute value to write this as x minus x0 absolute value times x plus x0 absolute value. And remember what I did before. Before I said that x and x0 both lie in the interval from -1 to 1 in the previous case. So x plus x0 absolute value, that quantity was no larger than 2. Unfortunately here I don't have this available to me because x and x0 belong to the interval from 0 to infinity. So x plus x0 can be arbitrarily large. So unlike in the previous case, x plus x0 is unbounded in I. Right, x0 is a fixed number that I chose, so x0 is fine, but x is whatever, right? It can be as large as I want. And so therefore, if I try to find epsilon, right, so if we want x minus x0 times x plus x0, if we want to be this to be less than epsilon, which is the same thing as saying I want x minus x0 to be less than epsilon over absolute value of x plus x0. Then basically this expression on the right hand side is not really smaller than a fixed number, because x plus x0 can be as large as I want, right? So that means that this will force x minus x0 to be arbitrarily small. So x minus x0 can be arbitrarily small. So that no delta not equal to 0 will work, right? For all x in this case. So what is the remedy here? So the remedy actually is fairly simple. So however, let's note that we only need to check or to work with x that are close to x0, right? So I just need to verify this property that f of x minus f of x0 is less than epsilon only for x that are close to x0, because continuity is concerned with what happens with my function at two values of x that are close to each other. And so because of that, we can assume from the beginning that x minus x0 is less than, let's say, 1, right? So I'm only looking at x, which are on a distance no more than 1 from x0. So if I can guarantee that as those x0 get closer to x, then f of x will get close to f of x0. If I can do that, then my function is continuous. Because I don't really care about x's that are far away from my original point. But if I do that, then if I go back to x minus x squared minus x0 squared, which is once again the absolute value of x minus x0 times absolute value of x plus x0. So now what I know? If x minus x0 is less than 1, that means that x0, that x differs from x0 by no more than 1, right? So then the largest my x plus x0 can be is what? It's the distance between them is no more than 1, so the largest absolute value of x plus x0 can be is going to be twice absolute value of x0 plus 1, right? Times x minus x0. now, just to illustrate how I got here, what is absolute value of x plus x0? This is x minus x0 plus 2 x0, right? Just subtracting x0 and adding x0. By triangle inequality, this is less or equal than magnitude of x minus x0 plus 2 x0, right? 2 absolute value of x0. And this, because I assume that absolute value of x minus x0 is less than 1, then this is less than 1 plus 2 times magnitude of x0, and that is precisely what I stated. All right, and so then 2 absolute value of x0 plus 1 is a constant. And so if I insist that original difference here is less, I want it to be less than epsilon, so I can just make the quantity that I just found less than epsilon, and it will guarantee that the original difference is less than epsilon. And so this would be the same as saying absolute value of x minus x0 is less than epsilon over 2 magnitudes of x0 plus 1, and I can call that delta. So as long as x minus x0 is less than delta, because of this implication that goes both ways, then x squared minus x0 squared is less than epsilon. And so the conclusion, for each epsilon I found delta, so that means that this function is continuous. So f is continuous at all x0 in I. All right, so now here does a common delta work for all x0? Doesn't look like it, because this expression, delta now, is going to be a function of x0. In fact, how should I go about finding the common delta? So x minus x0 is less than some quantity which depends on x0. So in fact, let's indicate this dependence simply by saying delta of x0. So if I look at 2 points, x1 and x2, right? So let's do that. Consider 2 points, x1 and x0, both belong to I. Then there is a delta of, in fact, again, if we fix an epsilon greater than 0, then delta of x0 is a delta that is going to work for delta x for x0, right? Delta of x0 works at x0, delta of x1 works at x1. Well, so if x minus x0 is less than delta of x0, it is going to work at x0. If x minus x0 is less than delta of x1, this works at x1. Can I choose delta in such a way that it would work at both x1 and x0? Yes. So if I make delta equal to delta, to the minimum of delta of x0 and delta of x1, right, then this common delta should work for both x0 and at x1, because if x minus x0 is less than the minimum of these two numbers, then it's less than delta of x0 at x0, so it works there. And it's less than delta of x1 at x1, so it works there too. So then this should work for both x0 and x1, right? If x minus x0 is less than delta, then f of x minus f of x0 is less than epsilon. And if x minus x1 is less than delta, then of course it's less than the minimum of two numbers. It must be less than delta of x1. So then f of x1, or f of x minus f of x1, is going to be less than epsilon, right? Okay, so if I have 2 points like that, then a common delta is a minimum of the two deltas. So continuing by induction, kind of, delta that works, let's say, for all, in fact, for x0 equal to 1, x1 equal to 2, x3 equal to 3, etc., for infinitely many points, delta that works like this, again, should be the smallest available delta out of those. And smallest available delta is the minimum or infimum of delta of xi. Right? And in fact, let's do the infimum, because I don't know if the minimum exists yet. What is it? So what's the smallest delta that works at 1, 2, 3, 4, etc.? That's a minimum. I belongs to n of what? What is delta of xi? That's a number that I computed here. So it's a minimum of epsilon divided by 2 absolute value of xi plus 1. And xi is an integer, right? So xi is, x0 is 1, x1 is 2, so it's I minus 1. So this is a minimum I in n of epsilon divided by 2 times I minus 1 plus 1. And what is the minimum of these numbers? Of course, I keep writing infimum, but it actually is a minimum too. But anyhow, so let's put the infimum to be consistent. And that infimum is 0, right? Because epsilon over 2i minus 1 plus I, when I is a natural number, is arbitrarily small. And so that means that common delta for all x greater than 0, or for all x in I, is equal to 0, right? Which makes no sense, of course, because you want x and x0 to be different, right? So if I'm saying x minus x0 is equal to 0, that means that x and x0 are the same, is the same number. And of course, if x is equal to x0, then f of x minus f of x0 is also going to be 0. So that means that there is no common positive delta in this case. All right, so can we interpret, so delta is equal to 0? It means that, in fact, what does that mean? Let's think about it. If I want to change my function by no more than epsilon, this says that at some points, changing x by very small amount should result in f of x changing by the amount greater than epsilon, right? Because if there is no common delta for all x, that means that always, no matter what delta I pick, always for some x, the difference between f of x, I can have x minus x0 to be less than delta, but still f of x minus f of x0 would be greater than epsilon. And that is a kind of, again, a statement about the rate of change, right? If I'm saying that x minus x0 is arbitrarily small, but f of x minus f of x0 is still greater than epsilon, that means that the slope of my function at some places should become arbitrarily big. And indeed, so let's draw a graph, just as we did last time, except that the graph in this case is not between -1 and 1, but it extends arbitrarily far away from the origin, right? So you have a function x squared which goes up like this. And again, so if I have x, 0 and x, f of x, f of x0. So I want this difference to be no more than 2 epsilon, right? Right, in fact, because it's x and x0, I don't want it to be more than epsilon. But as we keep going along the graph to the right, what happens to the slope? Slope becomes steeper and steeper. So then, if I impose the same, if I move the same window up, then the difference between x0 and x is going to get, so both x0 and x will move to the right, and the difference between them will be progressively smaller. So the farther up I send this difference, the closer these two guys are going to be together while moving to the right. So in this case, the slope slope of x squared is unbounded as x goes to infinity. Right? So as we look on the interval from 0 to infinity, slope is not bounded. So that means that as you keep moving your window up along the y-axis, again, as I said, the difference between x0 and x becomes arbitrarily small. And so that means that I cannot have a common delta. The common delta appears to be 0, right? Okay, so the difference, once again, to just summarize, the difference between the previous example and this example is that the graph extends all the way to plus infinity along x-axis and y-axis, and it doesn't have a bounded slope, And so that means that common delta is not going to work because I can achieve the difference between two functions being of some fixed size by taking two numbers, x and x0 and x-axis, arbitrarily close to each other, just as long as I move those two numbers sufficiently far to infinity along x-axis. All right, so then in the next installment of this lecture, I'm going to do a few more examples related to this.